So I'm going to talk about work that I've done with my PhD student, Ignacio Aravena, on solving stochastic unit commitment at industrial scale using parallel computing. And the focus here is a case study of the Central Western European market. So the motivation here is the different market design that's been adopted in Europe. In particular, a zonal market design has been preferred to the nodal US market design, which causes a lot of interesting operational side effects that have to do with coordination, but I'll make that much more specific later in the presentation. What we're basically doing is following up on work that's been conducted by Andreas Ehrenmann, Smears, and other literature on European market design, and more specifically, we're motivated by the fact that large-scale integration of renewable resources is making this task even more complicated. So on the one hand, we have the lack of coordination among European market zones, and on top of that, the large-scale integration of renewables. The combination of these factors makes day-ahead and real-time operation quite challenging. So we're looking to quantify how different the European system would have operated if it were organized the way US markets are organized in a fully coordinated fashion. This is our test case. So this is the Central Western European electricity market, and the title of the presentation refers to industrial scale because the model we're looking at encompasses 7 countries that consist of 679 nodes and 1,073 transmission lines, and I'll give you more specific details about the size of the model in terms of variables and constraints in the following slides. This is a breakdown of the fuel composition of the fleet. Here I just want to focus your attention on the fact that we are considering a large amount of both photovoltaic power production as well as wind power, and we are also looking at a 15-minute time resolution for our models. This extends the state of the art, which are typically hourly models for the types of studies we are conducting, and in particular what we're looking for are stresses on the system due to ramp rates, so due to abrupt changes in the output of power production. Of course, this increases the number of variables that we have to introduce to our models by 4, and here you see some typical realizations of renewable supply in our system. In particular, note the very abrupt ramp in the blue outcome over here. So among all the samples that we've used for our study, we're representing here the one that had the greatest 15-minute by 15-minute ramp, just so you get an indication of the stress that is being imposed on the system. The scale here is in gigawatts, so this jump, although it looks minor in that graph, is actually quite significant. So what I'm going to do in the talk is present at a high level a deterministic model for modeling US-type operations, a stochastic unit commitment model, which is even a further idealization of the deterministic model, and then the less ideal European models that we are comparing our performance to. And I'm also going to insist in a couple of slides on how we actually solve the stochastic unit commitment model through asynchronous algorithms. So going into the 2 ideal versions, the deterministic unit commitment and stochastic unit commitment, this is the setup for these models, and this is basically an attempt to simulate how a US type of market organization would have operated the network. So here what we are assuming is that the entire process is centralized and controlled by the independent system operators. So by the entire process, I mean that all parts of the supply chain are co-optimized at the same time. That includes reserves, transmission, as well as power production. And you'll see how the European setup differs from this. And when which basically amounts to a scheduling problem when you're deciding on that. It basically amounts to a scheduling problem, and we are considering here two different approaches for solving this scheduling problem. One is a deterministic formulation where we're optimizing our scheduling against a forecast renewable supply for the entire day, versus a model that endogenizes the representation of uncertainty by considering various scenarios of renewable supply over the entire day. So to get a sense of the size of these problems, just a single sub-problem for a single realization of a renewable supply outcome counts 444,000 variables, 539,000 constraints, and 9,552 integers. And as I will explain later, our approach for tackling this problem is a dual decomposition algorithm, where we basically consider each scenario independently, and we relax the non-anticipativity constraints, but which gives us a lot of traction. We can go a long distance in terms of attacking the problem in that way, but one complication here is that the sub-problems that we obtain have notably different running times. So there are some easy sub-problems that only take a few minutes to solve, and there are some more difficult sub-problems that can take up to 12 hours to solve. So what I did in my own PhD was to develop a subgradient algorithm that was synchronous, so it had to one iteration of the dual multipliers update had to wait for all scenarios to be resolved. What Ignacio is doing as an extension to this work is having the update of the multipliers be asynchronous, so you basically do not have to wait for all of the other scenarios to solve their sub-problem in order to update the multipliers. And I'll make this more specific in a couple of slides. So here's the prototypical stochastic unit commitment problem that we are solving. What you're seeing here is a minimization over production decision variable, which is represented by the P, which is a continuous variable, and then we have unit commitment and startup variables. Those are the U's and V's, and those are second stage decision variables. And we also introduce unit commitment and startup decision variables that are first stage decisions. So what we basically have is a partitioning of our fleet between slow and fast moving units. The slow units are units that whose schedule we have to fix 1 day in advance, and that cannot change. And to enforce that, we have this non-anticipativity constraint here that says that I do have a second stage decision for these generators, but whatever it is, it has to be for all scenarios consistent with the first stage decision. And what we then have to do is respect the minimum up and down times of these slow generators, as well as the operating constraints of all generators. That includes slow as well as fast moving generators. And we are seeking to minimize the expected cost of operation. So we have a discrete set of scenarios, capital S, each of which has a probability pi s, and we are minimizing no load cost, so that's the cost you pay for just running a generator, plus startup cost, plus variable costs that depend on how much power is being produced by the plant. And the strategy for attacking this problem is relaxing this non-anticipativity constraint over here. So that gives us a decomposable problem where we have a second stage sub-problems, and here is the term of the relaxation here and here that appears from relaxing these non-anticipativity constraints, so that we have a set of scenario-specific sub-problems, and then we have one single first stage sub-problem that only involves the unit commitment variables of slow-moving resources, and here as constraints we have the minimum up and down times of these resources. Okay. So this is the distributed algorithm that Ignacio has implemented at the High Performance Computing Cluster of Lawrence Livermore National Laboratory. The idea here is to break the computing task in various parts. So let me start from the dual sub-processes. Each of these sub-processes is solving a single scenario-specific mathematical program. One of these P2S's over here. And what it's doing is receiving multipliers for solving that problem from the coordinator, which stores the dual multipliers of all scenarios, and it's sending back its an estimate of the lower bound as well as a solution that comes up from the resolution of this optimization problem. This is a candidate schedule that is then passed to these primal recovery processes. So these are sitting in separate nodes of the cluster, and they are resolving a unit commitment and economic dispatch problem, but with part of the decisions fixed to what the dual sub-process recommended. So here, what these primal recovery components are also doing is, after they resolve, given a candidate schedule UL, they send back an upper bound to the coordinator. So the coordinator is checking by receiving lower bounds from the dual sub-processes, and by receiving upper bounds from the primal sub-processes is checking for convergence. Now, a standard block coordinate descent iteration algorithm, the way it would approach this problem is that you would basically solve so each of these components over here would solve its problem for the latest for the latest multipliers that are available, and it would also solve, so in fact, yeah, these sub-processes here are in fact solving two mathematical programs. They're solving this for a specific scenario, and this having stored the dual multipliers from all other scenarios of the problem. And by solving these two mathematical programs, we do a subgradient update to just update the components of the dual multipliers that are specific to that scenario. So this is what the task of those sub-processes is. Now, what we've done here is a tweak to that, because by doing that, we can definitely update the dual multipliers that are specific to our scenario, but one thing we actually miss is being able to compute a lower bound, because whereas our sub-process here has the multipliers available for all the other scenarios of the problem, it doesn't have estimates of the dual function for these other scenarios of the problem. So what we do instead is lag the input to the P1 sub-problem. So what we do instead is we keep the dual multipliers that have come in from other dual sub-processes at iteration k-1, because those come in not just with the multiplier information, but also with an estimate of the lower bound that is associated to that scenario. So in that way, what we are able to do is both parallelize the process as well as compute lower bounds at each iteration of the algorithm. So this is the modification here. So note the crucial part of the that differentiates this from a standard coordinate descent algorithm is the fact that we are lagging the multipliers coming from other scenarios than theta by one iteration back. And again, the goal here is to be able to compute a valid lower bound at each step of the algorithm coming from a specific sub-process. So that's been one approach that we have adopted to accelerating the algorithm. Then some other aspects of the problem that we've been attacking have to do with, again, lower bounding, but in fact accelerating the first lower bound that we are able to obtain from our algorithm. So As I mentioned earlier, some of the sub-problems that are scenario-specific can take up to 12 hours to solve. That means that even just getting the first lower bound can be a very slow process. So what we do in order to get our first good lower bound is we attack relaxations of the P2 scenario-specific sub-problems. And what Ignacio has done is he's considered two different types of relaxations. One is a linear relaxation of the entire sub-problem, and then the other is a time decomposition of the sub-problem, so considering each time period independently and ignoring intertemporal constraints. That's right, so okay, yeah, so that's as far as lower bounding is concerned. Then the other part of the algorithm that is worth noting here is that there's an accumulation of these candidate schedules that are sent back from the dual sub-processes to the coordinator, and the coordinator is lining up all these candidate schedules that are showing up asynchronously and sending them to these primal recovery nodes over here. One thing we are doing in order to shorten this line of candidate schedules that are lining up to be evaluated for upper bounds is we are using a result that was actually shown by Gustavo Angulo, where the result is actually quite straightforward. What it says is that if one of these candidates that have lined up is dominating other candidates that we've evaluated, by dominating that means that there's that this inequality here holds, and if that implies that the second stage cost of the dominating schedule outperforms the second stage cost of the dominated schedule, and this is quite intuitive for unit commitment problems because the more you commit in the first stage, and that knocks out your startup and minimum load costs, the less you are expected to pay in the second stage in terms of fuel costs. So that much is true for the problem we're looking at. Then that gives us a very quick way of checking a lower bound on our dominating candidate schedule by just evaluating this expression here. And as we've already stored this information, the only computation that is involved here is a summation and a maximization. So that's very fast to do, and that way we can discard some of these schedules that are lining up here to be evaluated in case they're not promising. So that's a quick way to prune our primal candidates. So these are some of the tricks, and I guess that covers the full list of tricks that we've thrown at the problem in order to accelerate its resolution. I now want to talk a bit about the scale of the problem and how it compares to deterministic formulation. So what you're seeing here are 5 versions of the problem we are considering. Deterministic 2R refers to a deterministic formulation which again represents an idealized case of coordination, a US-style organization of the market, but where the uncertainty is handled through reserve requirements. So these are extra decision variables that are introduced to the problem to reserve some excess capacity and make sure that if there's an uncertain realization of renewables, we can handle it. So whereas as opposed to the stochastic models that explicitly represent uncertainty through the scenarios. So this model is basically solving for the forecast renewables plus the reserve requirements. And this is with secondary, this is with secondary and tertiary reserve. So these are different types of reserve that can move faster or slower. And this is a formulation of that model with also primary reserve, which is the fastest moving reserve. So it's a slightly bigger problem, but actually the inclusion of that extra type of reserve really slows down the resolution of the model. And this is kind of consistent with what I mentioned earlier in terms, if you remember earlier, I mentioned what the size of a single sub-problem looked like in a stochastic unit commitment. So the numbers here look quite consistent because, again, we're solving for one scenario that's the forecast wind for the day. And then we have these three different stochastic unit commitment models where we're considering 30, 60, and 120 possible realizations of wind power production every 15 minutes until the end of the day. And here you can see that the size of the problem really blows up. It's specifically worth noting that we can, and you will see that we are able to tackle up to problems of these scales. That has about 53 million variables, 64 million constraints, and out of the 53 million variables, more than 1 million are in fact integer. This has been implemented in the Lawrence Livermore National Laboratory Sierra cluster, and we've been using Express on this jobs module, which allows easy coding of parallel algorithms. This is a specific way we've partitioned the computing among the nodes in the cluster. So what we have are 10 nodes for the stochastic unit commitment instances. So out of these 10 nodes, the 5 are dedicated to dual iterations. So those are were on the left side of the scheme I presented earlier, and the other 5 nodes are dedicated to primal solution recovery and upper bound computation. Those are on the right side of the scheme I presented to you earlier. Now, because of memory requirements, each node can run a number of sub-processes, but if you're running too many mathematical programs on the same node, eventually the memory of the node collapses. So we've had to do a bit of the P2 sub-problems tend to be more difficult than the P1 because they're optimizing for more binary variables. So we're allocating only 6 sub-processes per dual node, whereas we're allocating 12 primal sub-processes per primal node because those are easier problems to handle, and it accelerates the evaluation of upper bounds. Okay, so these are the solution statistics. So what we're seeing here is, of course, the deterministic model, you can't really parallelize it. We're just attacking it with Express. I'm reporting here the average running time, the minimum running time, and the maximum running time, as well as the worst case optimality gap. So why am I saying worst case? We basically, in order to simulate an entire year, we run one day type at a time, depending on what season it is and whether it's a weekend or a weekday. So that makes for 8 day types, and you're seeing here the best, worst, and average running times, as well as the worst case optimality gap. So right, and that's for the deterministic models, and then these are for the stochastic models and the different numbers of scenarios. And the 1 and 2 superscript refer here to the different types of lower bounding that I mentioned earlier. So again, recall that the first computation of a lower bound can take a really long time because a subproblem can take up to 12 hours to solve. So to deal with that, we either take a linear relaxation or we break time per time interval. So 1 refers to the linear relaxation for the first lower bounding, and 2 refers to the decomposition of the P2 subproblem per time period. So I guess the most important takeaway here, first of all, note how the running time jumps dramatically when we include primary reserve in the deterministic model. And we have imposed a 10-hour max wall time. So if we don't get the bound, the optimality gap that we're going for, which is 1%, then we just interrupt the resolution. So that actually happens in the worst case in the deterministic model. And then, by contrast, in the stochastic model, sure, there are situations where we hit our worst case running time. But it is worth noting that, for example, for the 60 scenario stochastic unit commitment problem, again, by dedicating 10 nodes to it, we are in fact able, on average, to solve these problems in 1.5 hours. And I think that's a strong message for practical applications, because this is more or less the running time that operators want to see for day-ahead routines. And it's also quite striking that it, in fact, runs in running times that are comparable to a deterministic model with just 2 types of reserve. So here, for all 8 instances, we're in fact within the 1% optimality gap that we're going after, and even in the worst case, we're not going to go above 5 hours of running time. If we give ourselves even more running time, then we can do even better. So note that here, yeah, well, or if we just relax this requirement of the 1% optimality gap. So for the toughest problem that I showed you earlier, sure, we weren't able to solve it within 1% within 10 hours, but within 8 hours, we can get up to 1.07% of optimality. And then the remarks I have here are one more thing that I forgot to note is that when comparing the 2 different ways of initializing lower bounds, you will note that the second approach of breaking the sub-problems by time period is actually much more effective in accelerating the algorithm. So that's another practical observation that came out of this part of the work, but the most important one was that we can actually solve these industrial scale problems within a couple of hours, which is what is operationally acceptable. This slide is to motivate the fact that there is room for improvement for dealing with the primal feasibility recovery. So a crucial part of the algorithm is not so much the convergence of the lower bound. That's kind of, in a way, if I dare to say so, easy, and people like Yuri have invented whole families of methods for doing that quickly. The trickier part is getting a good upper bound. So these scenario subproblems are sending large numbers of candidate unit commitment schedules, and these are basically lining up in our primal recovery nodes and waiting to be evaluated for their cost performance. So here's kind of a graphical description of what's happening. What you are seeing in the yellow is the number of candidates that have been evaluated, and that's measured in the right axis here. And you can see how the upper bound quickly drops as we are evaluating more and more primal candidates. But then the orange is the other primal candidates that are lining up behind them and waiting to be evaluated. And you can see that this is actually a logarithmic scale. So we have a serious congestion problem here. We've got, for every one candidate that's evaluated, there's 100 other guys behind him that are waiting to be evaluated. And it's really important to do this quickly because you see how effective this can be in closing, in rapidly decreasing the upper bound. So this is something that we've been scratching our heads about for a while, and we're looking for good ideas. I am severely over time, so I won't talk in detail about our simulations. I wanted to focus today, given the theme of the session, on the computational aspects of the work. Let me just leave you with one quick policy message from our work that I think is quite interesting. So, as I promised to you earlier, what you just saw was 2 versions of an idealized electricity market. One is the US type deterministic fully coordinated market. Then there was an improvement upon that, which was the stochastic unit commitment. But then there is the less idealized situation, which is the European situation, where we actually have a market that is highly balkanized in terms of how products are handled. So as opposed to the previous models that you saw, where everything is optimized simultaneously, with transmission, reserves, and energy being co-optimized, in the actual European setup, this is done sequentially. So we first deal with the transmission network. We input some of the parameters that have to do with the transmission network, that have to do with the capacity of the transmission lines, into an energy clearing auction. And then once that's done, we handle reserves. Now, in fact, the reserves are cleared in month-ahead auctions, so the actual timing of this process is before the clearing of the energy, but then agents can readjust in real time, so that's why we are representing that as a module here in the simulation of the European market model. But just for your ease of comprehension here, this is a modular representation of the European market reality that we will compare in terms of performance to the US type organization. And here are some salient features that differentiate the two approaches. So in Europe we run a power exchange. That's what they used to run in California up until 2001 when the market collapsed because of gaming. In the US type model we have an ISO, an independent system operator, that is coordinating everything centrally. So the power exchange is organized by simple bids, whereas the US type model is a pool where agents submit detailed information. Here in the US and the European model we have a sequential clearing of product instead of a simultaneous optimization, and we have a crude representation of the network through a zonal model as opposed to the US nodal model. And finally, there's this lack of coordination in the European setup. These two factors that are indicated in red are major sources of inefficiency. I don't have time to justify why they are major sources of inefficiency in detail, but I will throw at you some numbers before concluding my talk. So what you're going to see in the next slide is a comparison of the following models. One is a deterministic unit commitment. I already discussed about that, and the stochastic unit commitment. And then two types of representations of the European setup. One is a net position model that is closer to what's actually done today, where countries try to, in real time, be consistent with the net trading position that they took in the day ahead. So for example, if Germany promised at 11 a.m. today that they would export for each hour of tomorrow a certain number of gigawatts, when real time arrives, no matter what the renewable realization within Germany, they will try to stick to their day ahead position, which is not, it's fair to say that this is not a super crude approximation of what's being done today. And then there's a relaxation of that, which is the MC-free model, where regardless of what's happened in the day ahead, in real time, the zones coordinate in an adaptive way to the realization. So these are the numbers, and what I want to, well, let me quickly talk about these numbers. So these are the 5 policies that I discussed earlier. These are their expected costs, and we will measure everything with respect to the benchmark, which is the US type deterministic model. So that's our threshold here. And what we see is that moving to the European market coupling free design, we have a deterioration of 2.8%. The reason that's happening is because of a crude representation of the transmission network through a zonal network. And then if we move from MC-free to MC-net position, we have in fact a worsening of performance by 6.2% with respect to the deterministic unit commitment. And that is happening because of bad coordination among zones. And we're talking here about very real costs. This 6.2% translates to 650 million euro per year. By contrast, the benefits of having a stochastic unit commitment model are a 0.5% efficiency gain, which is overshadowed by these efficiency losses that are coming from bad market design. And in fact, the perfect foresight model can't do better than 1.1%. With that, I want to, and I have a bunch of analytics in the next 30 slides that I'm out of time, so we won't have an opportunity to discuss them in detail, but in the next few slides justify why these cost inefficiencies occur. But I'll just I'll allocate the next couple of minutes for questions. So thank you very much for your attention.